For over 100 years, physics has been living a double life. We have two incredible theories. General relativity, which describes the vast universe of stars and galaxies, and quantum mechanics, which governs the strange, tiny world of atoms and particles. The problem? They fundamentally disagree. Relativity says space is a smooth, continuous fabric. Quantum mechanics says everything, on some level, has to come in chunks. This is where loop quantum gravity, or LQG, comes in, offering a revolutionary idea. What if space itself is made of tiny, indivisible pieces? Imagine looking at a silk shirt. From a distance, it appears perfectly smooth, but get a microscope, and you'll see it's woven from individual threads. LQG suggests that if we could zoom in to an unbelievably small scale, known as the Planck scale, we'd see that space isn't a smooth backdrop. It's a physical thing, built from atoms of geometry. In LQG, these atoms are represented by something called a spin network. Think of it as a graph, where the intersection points, or nodes, are tiny volumes of space, and the lines connecting them. The edges are the areas that separate these volumes, and when these networks change and evolve, we get what's called a spin foam. This idea of quantized space allows LQG to solve problems that stumped even Einstein. In traditional physics, the center of a black hole is a singularity, a point of infinite density where the laws of physics break down. LQG avoids this infinity because space has a minimum possible size. The collapse of a star can only go so far. This has led to an even more mind-bending theory called loop quantum cosmology. It suggests our universe didn't begin with a big bang from nothing, but rather bounced back from a previous, collapsing universe. A big bounce instead of a big bang. So what are these fundamental building blocks of space? To grasp these, we have to let go of the old idea that space is an empty box. Planets and atoms, the box itself would vanish. Space isn't a container. It's a creation of the gravitational field. Physicists discover that the most basic components of this field are loops. Not loops of string moving through space, but loops of gravitational force that literally create space. These loops weave together to form the spin networks we talked about. Let's dive a little deeper into this architecture. Each node in the spin network represents a quantized chunk of volume, the smallest possible bit of somewhere. This means the universe, at its most fundamental level, is pixelated, just like a digital photo on your screen is made of millions of tiny pixels that look smooth from far away. Our universe only appears continuous because we read too big to see the individual pixels of spacetime. This granular structure isn't just a neat idea. One of the most radical ideas in LQG is what it says about time. When physicists wrote down the core equations for a quantum universe, they noticed something shocking. The variable t for time was completely gone. This is known as the problem of time. So, does time not exist? According to LQG, time isn't a fundamental aspect of reality. It's relational. We only perceive time passing because we see things changing relative to other things. The hands of a clock move relative to its face. There are only the quantum leaps of the spin networks, rearranging themselves. When a spin network changes its configuration, we perceive that as a moment passing. Time, in this view, is an illusion born from change. This brings us to the most exciting application of LQG. The Big Bounce. For decades, the Big Bang has been the ultimate origin story. But it comes with that pesky problem of a singularity, a moment where everything was infinitely dense and hot. Loop quantum cosmology replaces this with something much cleaner. As a previous universe collapsed inward, the atoms of space were squeezed tighter and tighter. But because space has a minimum size, it can't be crushed into nothingness. You can compress it, but at a certain point, the material itself pushes back. Once the universe reached an unbelievable density, gravity flipped from being attractive to being massively repulsive. Instead of collapsing into a singularity, the universe bounced. This suggests we might live in a cyclic universe, one that eternally expands and contracts, with no true beginning and no end. Now, the big question. How could we ever prove something so bizarre? The Planck scale is so small that no particle accelerator on Earth could ever hope to see it directly. But the clues might be written in the stars. One test involves gamma-ray bursts, the most powerful explosions in the universe. This would cause high-energy photons to arrive just a fraction of a second later than low-energy photons from the same burst. Our most advanced telescopes are searching for this tiny delay right now. Another clue lies hidden in the afterglow of the Big Bang itself, the cosmic microwave background. The Big Bounce would have left a unique set of ripples in this ancient light. If we can find that specific pattern, it would be the smoking gun evidence that our universe wasn't born from a singularity, but bounced back from what came before. LQG gives us a new story, not of a single bang, but of an eternal cosmic dance. Thanks for watching, and don't forget to like and subscribe for more journeys into the fabric of reality.